Good evening, everyone. Welcome to SLAC. It is my pleasure to welcome you all here, and it's always heartwarming to me to see an audience that has an interest in science, because the people here at SLAC, we put a lot of our time, effort, blood, sweat, and tears into it, and we always hope that what we do is of interest not just to ourselves, but the community at large. And you are fortunate tonight because today's speaker will be giving you a fascinating story with two key aspects of it that I think are quite exciting. The first, of course, is the science story he will be telling you, which is about the engineering, the fabrication of many of the attributes that we associate with human touch. But in addition, he will also be telling you a more personal story, which is about how one finds an interesting science problem and how you pursue it in sort of the day-to-day path to discovery. And I think both are fascinating, and I hope you both like them. Before finishing, I'd just like to emphasize that should we have an earthquake, you definitely duck under the desk in front of you, and when the earth stops shaking, there are exits behind you and in front of you, so to whichever one is most convenient. And in addition, make sure to keep the aisleways clear. And with that, let's begin our speech. Thank you.
Good evening, everybody. Thanks for the nice introduction, and thanks for coming out in that bad weather. Yes, the title is Engineering Human Touch. And I want to start this with a reference to George Lucas's space opera, Star Wars. I mean, there are many powerful images in these movies, but some of them can't be shown in this setting here. But one of the memorable developments is that at the end of the second movie, Luke Skywalker, the main protagonist, is fully confident in his ability to heads-on meet in battle the Dark Lord Darth Vader, and he has a fight with him with his lightsaber, and he loses it because he overestimated his abilities. And so during the battle, he loses his arm. And there's a very, very fascinating scene in the movie in which you can see Luke getting a new arm. And there are little actuators moving in there, and he can flex his fingers. And one of the visions that George Lucas had here was for electronic skin, because there's a skin coating that prosthetic that will give Luke a sense of touch. And he actually had a great foresight in many ways, because another memorable image is Luke's home planet with the two suns. And the surprising fact is that such a system has just this past fall been discovered by NASA. So more is to come. You have to dig into Star Wars and be inspired by all the things that future can bring. In this lecture, I'm going to be talking about artificial electronic skin. I'm going to give you a background. I'm going to focus on pressure-sensitive skin, the touch aspect. I'm going to introduce to you the two vehicles that we choose to make these sensors work, capacitors and transistors. And I'm going to introduce to you the technology that we choose to make a highly responsive and flexible, thin plastic pressure sensor that would be an artificial skin. And at the end, I will summarize and show, if I have time, a couple of recent examples of these kind of developments. Now, unfortunately, the medical field has grabbed the term artificial skin. I would have liked to call our skin artificial skin, but the medical artificial skin has been developed already in the 70s. And it's basically, and I'm just discriminating between the two so you get a better understanding what I'm talking about. It's a membrane, or most often it's a membrane, such as shown here, that is being put on the wound of a burn patient. And then either skin cells from the burn victim or donor skin cells that are grown into the membrane before it's being grafted on grow into that membrane, and over time, over many weeks, form a skin replacement. Now this kind of artificial skin has saved many lives during its, or in the past decade, and the rate for fatalities to of third-degree burn patients has gone down, I think, if I recall correctly, by 70%. So this is an amazing development, but it's in the medical field. And this skin is much more close to natural skin than the skin that I will be talking about, even though this skin also is thin, flexible, bendable. It will conform to surfaces, and it mimics important properties of human skin. And the signals that this artificial skin produces are electronic signals. So that's one of the key differences. Nonetheless, the inspiration for artificial electronic skin is still the human skin. And the human skin is an amazing array of sensors that provide us with all sorts of different sensor functionalities, such as pressure, temperature, vibration, and injury. And there are many different aspects to skin. For example, if you look at one of the hairs on our skin, at its root, there is a neuron. And when the hair gets deflected, we can sense that because that nerve fiber here at the bottom will transmit that signal. Now, likewise, there are dedicated corpuscles in the skin. They have all complicated names, Meissner corpuscle and Pacinian corpuscle. And they're, depending on which view graph you look at of skin, they aren't even in there. So the skin is so complex, certain aspects of its functionality keep being discovered. But for example, those two sensor cells, one is closer to the surface of the skin and detects one regime of pressure, more light touch, whereas the other one is embedded deeper in the skin and will sense stronger pressure on the skin. And there are also free nerve endings and all sorts of sensors in the skin to detect pressure, temperature, and so on. Now, in the following, I want to show you a couple of examples of artificial electronic skin that try to mimic these kind of functions. So my first example is a polymer skin that was developed in Oak Ridge National Laboratory. So, and I was asked when we rehearsed this, it was apparently unclear whether that's a real hand. But it's in a bag, so this is an artificial hand. But it looks very real. It's a polymer made to look real. And the one aspect that this group solves with this artificial electronic skin is the conductance of heat. Many times when you have a rubber or a polymer or these kind of artificial materials, they don't conduct current or heat very well. So when you have a sense of hot or heat on the outside of your skin, because it's thermally insulating, it may still be cold inside. And so when you wear this hand and you touch something that's too hot or may even burn your beautiful and expensive artificial hand, you won't sense it. Or the sensor that's embedded here at the bottom won't be able to quickly tell you that you're touching a hot surface. And so what they did is they loaded that rubber with little graphite structures that's shown here schematically. It's a scaffolding of carbon atoms known as a carbon nanotube. And they just put a whole lot of them into this rubber in a vertical alignment. And in this fashion, the carbon nanotubes act as heat pipes. And so if the surface is hot, now there are elements in that rubber that will conduct the heat. And so now the inside can sense this temperature. Another beautiful example, I think, is this of an artificial all-rubber hair cell. So this is bio-inspired. I showed you how our hair plays a sensory role in skin. And so these individual rubber hairs are biomimetically given sensor functions so that if the hair deflects by either a flow going over that hair cell or some kind of tactile impulse, then this is going to be sensed electronically. And just like the real hair that deflects and stimulates the neuron at the base of the hair, so in this rubber or artificial case, at the base of the hair here at the bottom, there are 4 sensors, 4 sensitive resistors that detect in which direction the hair deflects. And so this circuit knows if wind is blowing over that hair cell or if something's vibrating here. Now, an example more closely to what I'm going to be showing you later is this pressure-sensitive electronic skin that was reported by a group in Tokyo University. And they came up with this beautiful image here of this kind of film, plastic film, wrapped coiled into the shape of a hand. And each of these little structures that you can see here maybe, or here in the zoomed portion, is a pressure-sensitive pixel or sensor, if you want so. And the mechanism here is, and this is something that's going to come up later again, that deformation or a change in distance needs to be detected to produce a pressure sensor signal. So in this particular case, they have, again, a rubber. So in each of these pixels, it's a tiny little thin sheet of rubber, and it's loaded with graphite particles. So again, graphite, rubber, those are the two favorite ingredients of people working in this field. And when this gets compressed or pressed on, the rubber particles, the particles in the rubber will get closer together. And what happens when they get closer together is that the electrical resistance of this in this vertical direction goes down. So something that can be put in a circuit, a resistor, changes when this gets pressed on. And so the actual pixel is a lot more complicated. It has something that I will later describe to you how it works, a transistor. But the pressure-sensitive portion of it is put on top of it. It's something additional that's put on top of that transistor. And now I've shown you an example for pressure-sensitive electronic skin. I want to tell you what we think, or I think, this kind of skin is useful for, can be possibly find use and be used for in future. One interesting application was reported by a Austrian group. They envision shelves in a warehouse or a supermarket to be coated with a pressure-sensitive skin, and then you take your milk carton or a muesli box off, and the sensors in here would then know how many boxes are left on the shelf. So this is one interesting aspect. The much more obvious application would, of course, be something like robotics, where if you have a robot arm, such as this one, now you want to provide it with an artificial skin so it can sense its environment or can interact even with humans. So this we talked about at the very beginning, a coding for prosthetics. Another interesting application would, for example, be the coding of surgical instruments. So this is some work that was recently published by John Rogers from the University of Illinois. He imagines, or he actually realized, the coding of catheters for heart surgery to be coded by a pressure-sensitive artificial skin. And then that instrument would allow the surgeon to detect whether or not he or she is pressing too hard on a sensitive tissue. And this is so sensitive, it was even able to record the EKG of the patient just by the pressure changes or vibrations. And I found this on the webpage of Philips. Of course, in consumer electronics, you can imagine there's a huge or a large variety of possible applications for anything pressure-sensitive or a pressure-sensitive skin, or any artificial electronic skin. So they imagine you have an MP3 player or something that you put in a certain surrounding, and it has optical sensors, so it will find out like a chameleon how its surroundings look, and it will adapt. And you can imagine you grab it, and it feels the pressure and says good morning or hello or something like this. So definitely in consumer electronics also there's a big application for this. Now, what kind of pressure ranges are we talking about that we want to detect here? Our skin, the gentlest touch that we can sense, is on the order of 1 kilopascal or less. Pascal is the international unit for pressure. It will pop up every now and then. But so 1 kilopascal would be a very gentle touch. If you grab your coffee mug, depending on how early it is in the morning or how thirsty you are, you may have to grip a bigger or smaller mug, so that pressure is in the range of 10 to 50 kilopascal. If you work out and you grab a set of dumbbells, then you have to grip much harder, and the pressure on your skin would be in the range of 100 kilopascal, which incidentally is also very close to the atmospheric pressure that air puts on our shoulders. Now, human skin pierces at a pressure of about 3 megapascal. And then there's a horrible pressure that can be exerted by the jaws of a crocodile. Now, we don't want to make a sensor that works in this scenario, because if the crocodile got a hold of the robot, it's too late anyway. So we want to focus on this range here between gentle touch and firm grip. And we also wanted to find a method that can make this pressure-sensitive electronic skin inexpensive. You remember these commercial applications, shelving, etc. So this can't be too expensive. It needs to be cheap. And ideally, we would also be able to make it with we would like to use a technology that allows us to make it in a large quantity. So here's a picture of gigantic paper rolls. So this is a technology, the way paper is made, that if we could have a technology or offer a technology for electronic skin, that'd be great. So how do you construct a pressure sensor? How do you make one? Well, the recurring scheme I mentioned one time already is that you have to find a way to measure a distance change. Something happens to your sensor, and you have to somehow be able to detect it. Now, the archaic way of doing that would be to take a spring and a few steel rods and have something like this, now, and put a ruler next to it. And if you press on this, you would compress it, and then you can measure again, and you have a distance change. But this isn't very portable, and it's also not looking great on a robot hand. But something like this, we need to instill into the sensor that we want to make. So I want to show to you how we use two electronic devices. One is a little bit older than the other, the capacitor and the transistor, to turn them into pressure sensors. And the reason why we would like both of them is that the sensing mechanism here is a little bit more tricky. And so the transistor is the goal here in this development. But I want to start with the capacitor. So, and I will explain this as simple as I'm able to. The capacitor in the simplest geometry is a dielectric. That's a material that doesn't conduct current, sandwiched between two metal contacts. So that is already our capacitor, and these two metal contacts are linked to some power supply. If we apply a voltage to that circuit, what happens is that charges flow onto these metal contacts and start to charge them up. And you may have guessed that the device is called capacitor because its capacitance describes how many charges it can store. So it's something that stores charges. And one of the aspects of a capacitor that's interesting for our application is that its capacitance depends on the distance between these two metal contacts. If I bring those two plates, or these two contacts, closer together, the amount of charge that can be stored in the capacitor goes up. So the capacitance goes up as the distance goes down. And now you can imagine if you had a rubbery dielectric that can be compressed. If you press on this capacitor that has this compressible dielectric, now you would have found a way to translate the pressure into something electronically measurable, because now the amount of charges stored on these metal contacts has gone up as the pressure went up. And I already told you the transistor is a little bit more convenient ultimately when we want to actually turn this into electronic skin, because it's hard to count charges. I mean, it's quite possible to develop circuitry that reads out a capacitor, but much more convenient is it to measure an electrical current. A transistor, however, is not that much more complicated than a capacitor. In fact, it has one contact more, and it's in a way a fancy capacitor for simplicity. So again, we have one contact here, we have a dielectric layer, and now we have two contacts here, and an additional layer that's called a semiconductor. The semiconductor is a material that doesn't possess any free charges. But if you put charges in it, it can conduct those well. So, and now we have more contacts here, but that's about it. Vertically, this is still very much a capacitor. We just have this additional circuit here because we have two contacts up there. So now when we power this circuit here and measure the electrical current, we can't measure any current because, as I said, there are no charges in that semiconductor layer because we haven't put any in. But when we now, in addition, power this circuit here, we will, like in our capacitor, we will create charges on opposite sides of this dielectric. And now there are charges in this layer that can be dragged by this applied voltage. So in this case, when we switch this on and apply a voltage here, we can measure a current here. So in a sense, this circuit here switched on this circuit. And that's the fundamental role of a transistor. It's a switch. And all computer chips are made from transistors, tiny little switches that can switch their states between 0 and 1s. But so how now do we use this as a pressure sensor? Well, if we power both these circuits, we have a certain amount of charge in the semiconductor, and we will get a current in the device without any pressure applied to the device. If we now press on it, just like in the capacitor, we compress this dielectric, and we will have more charges. And the more charges that we have on this side here in the semiconductor layer will now make a larger current. So we'll have something where we can apply pressure, and we get different electrical currents. And that is what I was trying to tell you, the advantage of having a transistor. However, when we had this idea, so in our lab in chemical engineering at Stanford University, where this research came to life, we knew a lot about transistors. We didn't really use capacitors very much, but we didn't know anything about electronic skin. But we visited the robotics department, part of the, I think, the mechanical sciences department. And they are interested in all sorts of robotic applications. They make little spiders that can climb up walls, etc. And we were looking to foster some kind of collaboration. So we knew about this, and we had no idea how we could possibly help them. But they had a lot of rubber lying around. And on our way back, we had this light bulb. What if we had a compressible gate dielectric that we never thought about to make squishy? And so this was the idea. And of course, in the beginning, we were very enthusiastic, and we were looking around in our lab, what material could we use to use as a compressible rubber, compressible dielectric. And it happened so that we have a material that we actually used for molding. So we used this silicone material here for a different purpose. That particular material that's abbreviated PDMS is used widely in all sorts of applications, such as sealants for aquariums, silicone cork containers, and nipples for baby bottles. The clear type are made of this material. And to my shock and horror, it's actually also used as a food additive. And I only found that out preparing for this presentation. And I think this gives another dimension to a casual remark such as, oh, the chicken's a little rubbery tonight. But so the low-hanging fruit for us to test whether we can make a pressure sensor using this rubber in a capacitor was to just make the simplest possible capacitor. It was a really coarse-looking, really not very refined-looking device. This is the original that I made many years back. It's basically two metal contacts, gold deposited on glass, and sandwiched between those two is a thick sheet of that rubber. It was 3 millimeters thick. But it was it turns out it was a working pressure sensor. And back then we didn't have a fancy way of applying loads and measuring variations in the pressure applied. We just had weights. So we glued little glass marbles and made little weights to apply on top of this structure and test how well it's working. And so that's what you're seeing here in this view graph. Here you see the change in that capacitance. And here that's just the number of experiment where we put different weights on the capacitor. For example, that first data point here, we put a bigger weight on there in this first loading cycle. Then we take it off. So we go back to this green data point here, which shows a nice 0 capacitance change, meaning the device goes back to exactly the state it was at when nothing was pressing on it. And we tried another weight, and it can't be seen in this view graph, but the sensor was very responsive. We looked at the capacitance meter, and it went right back down. So we were very enthusiastic and thought we are having a killer idea here. Now, of course, to make a transistor or to make a feasible capacitor, we need to make the rubber much, much thinner. The capacitance that this device would have is very, very small. It's so small you couldn't feasibly detect this in a skin application. And for the transistor, this needs to be about 1,000 times thinner. So we need to reduce from millimeter to micrometer. And of course, we did that in the second test. So the same kind of device, even same dimensions laterally, but the rubber was much thinner. So now we had only a few micrometer thick rubber. We did that same test, and we immediately noticed two things. First, the change in capacitance with the same weight applied was much less. Well, that's disappointing, but it's not yet killing your enthusiasm. But the one thing that was really a problem is that when we took the weight off, the capacitor didn't go back right away to the unloaded signal. It slowly crept back. And you can see this here, for example, when we have the bigger weight on, and then we take it off, so we arrive at the next data point. And this should be down here at 0. And even if we measure multiple of these a few minutes apart, it still kept slowly creeping. And so I have one more curve that shows the same thing, basically. We started with this weight. So that's here. We take it off at time 0. And then the signal slowly crept back. Now, we have the same experience with our own sensors. You know, if you look at an intense light source and you close your eyes, you see this little ghost image of your light source. So we have this kind of fade effect or a creeping behavior in our own natural sensors. But of course, we want to make a sensor that can immediately sense that that pressure has been taken off the skin or something else comes on. We can't wait 3 minutes for the sensor to recover. So this was something we needed to understand at a fundamental level, what happened. And I want to try to walk you through this a little bit. So when you have a pressure, when you have a rubber cube, we all know from experience when you squish that, it buckles out. It will deform, and its sidewalls will deflect outwards. And in a way, this behaves like a spring. So the sidewalls buckle out, and store that energy that you impart on the system. And when you release the pressure and you take that weight off, that spring will relax, and it will bounce back to the shape of a cube. Now, when you have a thin film, this doesn't work so well, because the height of that film is much, much less than its width. So we almost have no sidewalls. We almost have no surface area that could buckle or deflect. So most of the volume is in the film, and there's almost no surface. So that is a kind of intuitive insight that there's some difference between this and this. But if you discuss this at a microscopic level, it's also relatively easy to explain. Rubber consists of long, floppy chains of atoms that are relatively loosely packed together. And the only thing that holds them in place are these little links here. And so when you make a rubber, you typically start from a base and a crosslinker in the same way that when you make epoxy glue at home, you have a base and a crosslinker, you mix two things, and after a while it hardens. It's very, very similar. And so when we start with the base of our rubber, it's like honey. It's viscous, and it's almost like a liquid. But once we cure it by adding this molecule to it, it will anchor the molecules, tether them together. It will grab them in different places, and that gives the rubber its consistency and its solid behavior. When you now put the weight on, what happens is that before you put the weight on, the molecules are in a state that they like to be in. They naturally find a way of arranging themselves in the way they like to be in. When you now compress, you shove these molecules closer together, they will react to that because they don't like to be that close. So when you do that, they will displace and slightly push outward. And of course, many millions and billions of molecules do that, and you get this buckle here in your rubber cube. Now, when you do this in the thin film, even if you start with the exact same rubber and you were magically looking at an identical spot of structure, what happens is when you compress this, there's no way for it to displace material because it doesn't have much surface to go to. And so what happens is those molecules are pushed closer together, much closer than in this case, and they get hooked together, they get entangled like spaghetti in a pot. And so now when you take that weight off, they can't find their way back immediately to that relaxed state. And so this disentangling of the molecules is what takes the time and what produces this slow creep of the rubber back to this relaxed state. Whereas here, the deformation and displacement is small enough that it bounces right back when we take the weight off. So now we understand the fundamental microscopic or nanoscopic, if you want, issue that's underlying the poor performance of the thin film that we need to perform better. And so what are we going to do about these points? And how are we going to make this thin film behave more elastic? Well, we can, the only thing that we could come up with is we need to create many structures that are more like a cube, or that have the same height and that roughly the same height as they have width, and lots of free area to deform by removing material. So we need to somehow remove a lot of material, and that way generate many, many, many structures, each of which now can behave like a cube or like something that can elastically deform. So when I press on this structured or microstructured rubber film, the hope is that each of these individual little pyramids here will deform elastically in its shape. It has lots of free surface to buckle out. And I have to defer the question that popped up in your head, why are we now at pyramids and not at cubes? We just talked about cubes in a moment. But the point here is that we need to create a lot of free surface to promote this elastic response. We need to have lots of little features that each individually is looking a lot like a cube or has the same roughly width as it has a height. And so the one way that we envisioned doing this was to mold. But before I get to that, I want to show this slide also for our younger audience. Basically, our idea, as proud as we are of it, isn't so unique, because nature has gone that way in a very similar fashion. If you look at a sponge, if you take the material of a sponge and you would make a solid brick of it, it wouldn't be elastic like a sponge in your kitchen. But when you zoom into SpongeBob, there's the material, that's the rubber, and then there are many, many voids, bubbles, holes. There's nothing there. And what these bubbles or these voids do is they partition the rubber into areas that all have lots of deformable surface. So each of these light yellow structures here can deform and extend into the voids. And basically, the bubbles partition this sponge material into areas that have roughly the same height as they have width. So what we have done here, or what we want to do here, is making a two-dimensional sponge artificially. And the way we went about this, we thought, how do we make tiny little structures on a micrometer scale? Well, we wanted to mold PDMS. This rubber is known to be molded very easily. In fact, I have a piece of this rubber here in which, over the weekend, I molded the impression of a $1 coin. And you're free to come here after the presentation and look at it. The ability of this material to serve as a molding material is very good. And that's why we had the material in the lab to begin with. So how do we make a mold for rubber? We use a method that's well known in Silicon Valley, photolithography. That means structuring with light. So this is essentially the technique by which almost all computer chips are made. So I most likely have experts in the audience that know much more about photolithography than I do. But what it starts with is a silicon wafer, some silicon substrate. And what you do is you coat that substrate with a substance called photoresist. It's just another film of another material. And then you hold a shadow mask. It's typically metal with some windows in it, very close to that photoresist, and shine light through it. And what then happens is that the photoresist gets exposed to the light in places where you had a window in the mask, and in the places that are shaded by the mask, it doesn't get exposed. And exposure to UV light changes how easy the photoresist gets washed away or dissolved. So when you now have this exposed photoresist pattern, and you wash it in a special solvent, it will wash away the photoresist everywhere where it was exposed to the UV light. And what you then have is essentially another mask, but this mask is directly on the surface. Basically, you have a patterned surface of exposed silicon surface and photoresist. And now we want to use this photoresist mask to etch pits into the silicon. So we use a powerful etchant that can etch silicon and expose this whole surface to that etchant. And everywhere where we have exposed silicon surface, it will etch a pit into the silicon surface. But the etchant, potassium hydroxide, doesn't attack the photoresist, so all these areas remain protected from the etchant. And when we then wash, at the final step, the remaining photoresist away, we have made ourselves a mold. Because we have tiny pits, I mean micrometer-sized pits on the silicon surface, and now we can press the rubber in that and use it as a mold. First, I want to show you how our molds look. We got these beautiful looking images under an electron microscope. You can see thousands of these etch pits here in a regular array. So each of these little things is one pit etched into silicon. And here you see a zoomed in area. And here zoomed in again on one single one of these pits. And here I arrive at the point where I can explain to you why we have pyramids in that cartoon and not cubes. This particular wafer that we use to make the mold is cut from a big silicon single crystal. And you can cut that single crystal under different angles and give basically the wafer different crystallographic cuts. And depending on what cut you have, the etchant doesn't eat vertical sidewalls into the silicon wafer, but it may etch a pyramid, basically a sloped wall into the wafer. And what you see here, these black lines, are basically the edges of a pyramid that's pointing into the silicon, an inverse pyramid that's going into the silicon surface. And technologically, it's easier to make the mold that way, and it's much easier for us to control the quality of all these little pits when we go with this wafer cut, and that's why we have pyramids. Of course, the mathematically gifted among you will also say, well, the pyramid also has more surface area per volume. We can make pyramids. We can also make lines with a triangular line profile, and we can actually make cubes. It's just harder and to make the cubes, and the quality, the yield from these molds is not as high. So now we have a mold, and in a way, it's like a muffin pan. So you put now your dough into that mold and make muffins. In our case, we do the same thing. We need to make it non-sticky. Like you would, if you have a muffin pan, you would put some butter or grease on there first. So we spray something on there that's a lot like Teflon to make it non-sticky. And then we cast our still honey-like base of our rubber onto that mold. And we press on it, and we flip the substrate on it that we want to transfer those little pyramids onto. And that's typically a plastic film. We press and we heat that, and so the rubber cures and turns solid. And when we now lift or peel this off, all these little rubber pyramid muffins stick to our plastic film. And we get a quite beautifully looking film of many, many microstructures. So these top two images here are looking at this microstructured rubber under an optical microscope. And you can see here where it's a little rolled up, you can clearly see the shape of these pyramids. And this here is a top view onto a film that we have lifted off, again in the electron microscope. And now these pyramids are sticking out of the board and look at you, and are rubber pyramids. You can also see we get a little flattened base here. That's technologically a limitation of the way we etch. It never meets in a sharp point. It always makes this little flat base, but we get these nice pyramids. And I show you this image because you can see here with what quality and fidelity we are able to make these. So what you see here is a film of this rubber, with these rubber pyramids, and here at the bottom of the image is the edge, and so the film hangs over there. And it's slightly blurred because it's not in focus. But what you can see here, you see the individual pyramids. And then when we look overall more from the side, you can see how all these pyramids line up. And their tips basically are just visible like lines because they're all of exactly the same height. And this is what we want to accomplish. We want these microstructures with as much quality as possible. Now, this is a lot about chemical engineering and engineering. However, I work at SLAC at SSRL now, so my daily business is diffraction, X-ray diffraction. So I just couldn't resist the temptation to show to you the quality of all these pyramids by doing a little diffraction experiment. What happens is when you have regular features in an array on the length scale of a few micrometers is you also have an optical grading, which means that if you send a laser beam through this, it will get kicked in all sorts of directions. It will not go just straight through, but it will get little kicks, and it will make a beautiful pattern of spots if you project it. And if you could dim the light. So I want to try and, so I have here a sample that contains all these little pyramids in one of these regions. And I hope I will not blind anybody here, because I just shine through this. And what you can see here is that I get a beautiful diffraction image. And I see, what you can also see here, in these fields, we have slightly different sizes. They make different patterns, but it's very beautiful. And so you only got to see this because now I work at SLAC. Can you restore the lights? So we have a very, very high quality film of these tiny microstructures. And we're ready to measure. And before we get to the results, I just want to show you the setup. By the time we had solved this issue, making all these little microstructures, we also had a much, much better setup that the student that did a lot of work on this project set up for us, which is a force gauge that you can see here. It has a little metal pin, and here's our sample. And now there are lots of wires and cables, and we read the capacitance out of this instrument here. And here you can see a zoomed in portion of this sample under the pin. So here's our plastic film, and then there's this structured rubber, and there are electrical contacts and a pin that's pressing on it and applying different loads. And so now here's how the sample looks, and here's how it has improved over the solid film that I showed you earlier that we set out to correct or improve. So here's again capacitance change. And so now this axis isn't individual weights anymore or number of experiment, because now we are able to directly increase the pressure on the device using that force gauge. So when this axis here basically shows increasing pressure. And the green curve here is our microstructured PDMS pyramid film. And the red symbols here is a film that's of the same height but solid. And as you can see, we have drastically improved the response of that film. By application of a pressure of, well, we have gentle touch here. So once we apply several kilopascal, we change the signal by 100%. We doubled the capacitance of this signal. And what about the other problem that we had? When we took the load off, it took forever for the sensor to recover. So here you can see the load being put on the sensor, and then it sits there for 4 seconds. And now you see two curves, one of the unstructured solid film that's still showing this ugly creep back to no load value. And here's our structured rubber. And pretty much within the resolution of this setup here, it falls right back to idle. So we estimate that the response time here is on the order of 100 milliseconds, which is as fast as human skin can sense anything. So that worked great. Now the question is, how mechanically stable, durable is this microstructured rubber? So we also did a couple of experiments where we take this capacitive sensor here, and here's the structured rubber field, and we bend it. And we bend it thousands of times, and we see whether the signal is deteriorating. Because, of course, in a real-world application, you may have wrinkling or bending, and it shouldn't destroy the device. And without explaining too much detail of what this shows here is, this here shows how many bending cycles the device has endured. And from the fact that these lines here remain horizontal, I hope I get you to trust me that this means that the device is very stable. And here you see a similar mechanical stability experiment where we now lower that pin many, many thousand times to see whether that over time will destroy the signal. Of course, we can't have that if we, after 1,000 shakes, our hand doesn't work anymore. So, what you can see here is that the signal remains very, very constant over 10,000 cycles. So we're also happy with the mechanical stability of this microstructured rubber sensor. Now, this was a lot about the capacitor, but of course we also set out to show that we can use a transistor to turn a transistor into a pressure sensor, because you will recall measuring current in the long run is a better concept to electronic skin. And so this looks a little complicated compared to what I showed you earlier, but it's essentially the same. I just have to flip that upside down, because that's how we built that device, so that we can put the weight on top. So we have our two contacts here, source and drain. There were these two contacts here. Then what was purple here, now regrettably I realize I have a purple color here, but this, what's purple here, is that material here that we put on top of these electrodes. That material is an organic semiconductor called rubrene. And now we need our squishable rubber dielectric and a top contact. And that's this here. So we have these structured pyramids that we put upside down with a conducting plastic electrode. And we put that down on the sensor and then apply weight on the surface of this electrode. And you remember I showed you this curve here. What we expect this transistor to behave like is that if we apply pressure, because we get more charges, we get this kind of response where we now have more current that we can pull once we press on the device. And this is what we measure in the real device. So this curve here at the bottom shows the curve at no load. That's, of course, I made it to look very similar, but the effect is here. And now you can see that when we put more load on there, we get this kind of curve. And so we have successfully demonstrated that we can make a transistor where an integral part of the transistor, not something that we put in addition on top of it, an integral part of the transistor is compressible, and therefore the whole transistor turns into a pressure sensor, and a very, very sensitive on top of it. And so, of course, we thought, can we push this to the extreme? What's the smallest pressure we can detect? And so we ordered the carcass of a blue bottle fly, because that was just the smallest thing that I could imagine, or we could imagine, that I were still able to show you in a view graph. But still, it would have a very, very small pressure. And mind, even though the fly has legs, and because the legs have a much smaller area by which they touch the surface, you would get higher pressure, just like a needle applies a high pressure. We put a glass plate in between, so that actually the weight, this tiny weight of the fly, acts on a large surface. It's a tiny pressure. It amounts to 3 Pascal. And what you can see here is the capacitance of this pressure-sensitive plastic film when we put the fly on. And we leave it on there for a while, and here we take it off. So we can clearly, without much noise, discriminate between this tiny load and no load. And because this is such an amazingly small pressure, I thought I'd give you a feeling for how little a pressure this is. Excuse me, at the last World Cup in soccer in South Africa, a musical instrument became infamous for being very loud and annoying. And so, but I found a value for how much sound pressure it creates at a certain distance. So I calculated that 3 Pascal corresponds to standing 7 meters, that's close to 7 yards, away from the opening here. But you wouldn't have ears. You would have that sensor, and you would be able to tell, using your electronic skin, that somebody's playing that instrument. So that's how tiny that pressure is. And it was very technical up to here, and to reward you for hanging in there, I want to give you a little bit of comic relief. Fortunately, we were very honored to find that we were properly and skillfully made fun of by in the Colbert Report. And so let me play this little clip. This is only a tiny snippet. I can't show the whole thing, it would be too long. But at the beginning, it features the work of an Italian group, which was too hilarious for me to cut out and just show ours. So they came up with a robot that can shoot arrows, and it's just really fun.
And now, European researchers at the Italian Institute of Technologies, the same people who weaponized the cannoli, have taught a robot how to kill. This cybernetic savage can accurately aim a bow and arrow at a target in just 8 tries. Just think how dangerous it would be to stand still in front of it for about an hour. Now, I'm sure you're all saying, Stephen, it's not like these robots have become self-aware. You fools! Researchers in California have now invented robot skin, which can sense pressure as sensitively and as quickly as human skin. And folks, if robots have skin, for the first time, they can be naked. Floppy drive hanging out.
And this is where we cut out and move on. So let me summarize the research that I've shown you. What we accomplished is we developed a highly sensitive, highly responsive new e-skin technology that can sense pressure very well. It's all plastic, mechanically stable, and it flexes. Now, what I will honestly state here, we haven't quite solved with what I've shown you so far, is to make this into a high-resolution matrix, where we now would take the transistor that we made and make it tiny and make a huge array of it so that we have like a pressure display. But the good thing here is that all it took for us was to show that you can make a transistor into a pressure sensor. And other people are very good at now taking the idea and making the actual transistor really small and making it into an array. So this kind of know-how exists. And while we don't have it in our lab, or didn't have it in our lab, this is not a showstopper. PDMS is a biocompatible, eatable material. And the molding is an inexpensive and scalable technology. I mean, this is something where you can envision, you can make a large waltz and make it reel-to-reel if you perfect it. I also haven't shown you the operation of a transistor that operates at very low voltage. Well, I haven't really told you what voltage we apply. I mean, so the smallest voltage we could apply and still get a good signal out of the transistor sensor was 20 volts. While I in school got taught that only 40 volts are lethal, you have a hard time telling people to deal with a robot that touches you and mildly electrocutes you if you don't encapsulate that skin very well. So of course the skin would be encapsulated and the electrode would be on the opposite side, but people would maybe feel uneasy. So clearly we need to bring that voltage down, especially in applications where people interact with electronic skin. But again here, the same thing holds. There's technology out there. People know how to reduce the operating voltage of such a transistor. The material we used, it works well for us, but it's by far not the best to make a really low voltage one. And so there are, like these carbon nanotubes I showed you in the very beginning, they're good to make a device really low voltage. And so this is also very straightforward development. And of course, the big target that's quite a few years away, at least from our point of view, is how do you maybe offer an alternative to this actual artificial skin that I showed at the very beginning that takes many weeks to heal. So is there a path where you can take skin like this and at least temporarily give the sense of touch to a human being, or somehow interface with our senses? And so of course to solve this, you have to bring down the electrical output from your sensors to a level that our nerves and our brain can manage. And so this is a very different world. So the output of our nerves, they operate with millivolts and very, very small currents. So of course this development is still far out. And if I have a couple of minutes, I will just show you briefly one or two applications that have emerged since we finished this research in 2010. In fact, the group in which I did this research on the results I showed you, in the meantime, they were not resting on their laurels. They came up with a new sensor. Now, in this particular application, they made it all transparent. While this is less important as a feature to skin to be transparent, the material they used is also very stretchable. So what they showed is that they can make the sensor extremely stretchable. They can stretch it out to, I think, 3 times its size, and they can let it bounce back, and it will still work. The sensor, in order to have this incredible stretchability, has much less sensitivity, but it's clearly one of the components that one wants to look for in order to have a successful artificial skin, that you are also stretchable, not just bendable. So their sensor, they have to apply megapascal. That's close to the piercing pressure of skin to get a good discrimination of levels here. But it's a good step. So in this sensor, again, carbon nanotubes are being used. So these little coils that you see here are all carbon nanotubes. So there's something about graphite or graphite materials and rubber that is just magic in this field. A really cool application is also maybe a little scary application, if you feel that way, is this e-tattoo. So this is a work that was, again, the same group that put the electronic skin on the catheter surface for the heart surgery. They came up with a very similar concept, but have this beautiful idea to make a tiny tattoo that you can put on the patient's skin. And there's all sorts of functionality in that electronic skin. There's a wireless power coil, so you're being powered by some remote radio power source, and all of a sudden the LED lights up on your tattoo. But you have a lot of functionality here. This thing can take an electrocardiograph of the patient, and it can even discriminate when put on the throat. It can discriminate spoken words, up, down, left, right, and they control the computer game using that tattoo on a person. And of course, it's one more step in the direction of Big Brother, and it's cool now. And in 20 years, when we are forced to wear it, it's less cool. But I found it too amazing to not show that to you here. And with this, I want to acknowledge the 3 people without who this research would absolutely not have been possible. So my postdoc advisor, Professor Shinan Bao, in chemical engineering at Stanford, who was my PI during that research. Benjamin, who joined our group as a grad student and then joined the project, and he was instrumental in building this beautiful measurement setup. So basically, without him, we would still put the marbles on the sensor to put a weight on there. So he came up with this force gauge, and Dr. Stoltenberg helped a lot with these electron micrographs. He provided these beautiful views on these tiny structures that I was able to show you. And Roger, who's a current student in the group, I came to him 2 weeks ago. I said, I need something to shine a laser through. And he let me borrow this one because I don't have any of my old samples left. So thanks, Roger, for letting me have this demonstrator. And thanks a lot for your attention.
Let me start by thanking you, Stefan, for a very entertaining and informative discussion. And with that, I would like to open the talk to questions from the audience. So what we're going to try and do is there are microphones. So please wait for the microphone before you start asking your questions so everyone in the audience can hear them. And raise your hand, and I'll try to get to everyone. So the first hand I saw was right here.
Any thought to putting these things on spacecraft so that we can extend telepresence into the solar system? And even maybe spy robots and who knows what?
So the question is, any thoughts about putting these sensors on spacecrafts and spying on alien worlds? It's definitely possible. I mean, I don't know so much where we would send our spacecraft in order to spy on somebody, because I don't think we have the vector to that world yet, but those devices could definitely work in vacuum, if that was your question. So in the vacuum of space, they could easily work and would work just fine. Sure, if we needed some sense of pressure to certain instruments on a Mars drone or a robot, yes, absolutely.
So my question has to do with fabrication. You use silicon wafers to do the pits, but that's not really a very suitable material for doing very large things, since silicon wafers only come in dinner plate size things. How dependent is it on that, and how hard is the molding process on the mold itself?
Well, so the question is, we use a silicon wafer as our muffin pan. And so the silicon wafer is very rigid. And so the question is, how can this possibly scale to something large in terms of high throughput fabrication? Well, the good news is that you really only have to do this once using the silicon. Because in fact, you can mold PDMS with PDMS. So you can make a mold out of PDMS and coat it non-sticky, and then pour PDMS on that and lift, and you would still get that. So you could make a mold out of a plastic or polymer material that's more suitable to be made on a large scale by initially starting with silicon, but then you don't need silicon anymore.
On your little lights out demonstration where you showed the laser through the, how does that react with other forms of light that are non-coherent, like incandescent, fluorescent, neon, and all this kind of thing?
Yeah, so the question is, I only used, used a laser pointer to shine through my optical grating. And so the curious question is, what would happen if you didn't use light of just one color, like in a laser? Well, I invite you to convince.
More important, non-coherent versus coherent.
Yes, non-coherent. You can convince yourself of what happens by, I invite you to come down when we're done. If you look through it, you get these prism effects that you get from gratings, like you see a little rainbow, and you turn it, and the rainbow kind of colors move around. So you get the regular interference, fringes, and this rainbow effect from white light.
Have you done any mechanical stability tests with it built into with the FEC as well, not just the material?
No. So we have only bent the capacitive sensor. But again, here I kind of cheaply defer to existing knowledge about these organic field effect transistors. So in fact, in our lab, we make all plastic organic field effect transistors that have to endure that very same bending process. And we have a little stepper motor that runs overnight and bends that transistor to about that same radius, which was arbitrarily chosen to about the curvature of a pinky many thousand times. And so it's not an issue, because the organic field effect transistor that we were using, especially when you also use organic electrodes and not gold, like we did for convenience, is inherently also flexible, because these materials are, in a way, plastic materials.
Yeah, so how would, I'm over here.
Yes.
How would you integrate the other three forms of touch, sense, I guess you would say, into an e-skin film? How would that work?
Yeah, that's a very good question. So, I mean, the way that I think about this is that when you make a matrix of pressure sensors, that you don't make, if you can make them dense enough, that you don't have to make neighboring pressure sensors. But what you could do is you could make one sensor or pixel a pressure sensor, and the neighboring one would sense temperature. And then maybe every now and then, every, let's say, 10 pixels, you would have a hair cell or something. So you have this modular design if you have a matrix. You could definitely do this if you have enough resolution. If you can still put the points that sense pressure dense enough that you roughly emulate, the sensitivity of skin. And we definitely think we can do that. I mean, especially the children among you who are curious to experiment, I invite to do this experiment when you take two pencils, equally sharpened pencils, and you hold them as close together as you can. Of course, if you touch the two pencils, if you press the two pencil tips against your fingertips, you can definitely sense two tips, because we have a very, very high density of nerves in our fingertips. But for example, when you do this on this portion of your arm, you will only sense one point. You can't discriminate between the two. So the fingertip is in a way the benchmark. And the density of pressure sensors that we could do with only micrometer-sized posts, we can definitely achieve the density that we have in our fingertips, which is the highest that you would have to look for. And then you can now start to replace individual pixels with temperature sense and all the other functionalities.
In the middle here.
How do you embed the carbon nanotubes into this structure so that they're all pointing the same way?
Oh, yeah, that was the application that I just showed. Well, I have to admit to you, as proudly as I showed this, I haven't really dug into the fabrication details of that sensor. But typically, people use patterning techniques if you, for example, bring on the carbon nanotubes from solution onto a substrate, you can make the substrate repelling, de-wetting or repellent to that solvent in which your carbon nanotubes are suspended. And so then you can basically pattern some stripes of attracting the liquid, repelling the liquid, attracting, and so on and so forth. And when you now pour a solution that has something suspended in it that you want to pattern over such a pattern structure, then it will basically wet only every second row. And now when it dries up, it will only leave carbon nanotubes behind there. Something like this, I can imagine, led to this kind of patterned structure.
All right, with that, I'd like to invite all of you to join me in thanking Stefan again. And I suspect that Stefan would be willing to answer a few questions if you were shy about asking them in front of everyone else. And thank you all for coming.